Hi, my name is Dave Wu, and I'll be hosting this podcast series on water treatment solutions. As you know, our entire existence depends on water. In a given day, the average American uses about 6,800 liters of water, and that translates to about 2.2 trillion liters per day in the United States. And on a worldwide scale, that translates to 9 trillion liters of water per day. Well, that's a lot of water, and it's got to come from somewhere. And when we use it, that water needs to be treated before and or after human use. It's for this reason a whole industry has been dedicated to treating our water and to make it safe for consumption and to make it safe for releasing it back into the environment. This podcast series will cover water treatment using membrane filtration. Today's segment is dedicated to water reuse. What's water reuse, you may ask? Well, water reuse is treating water from municipal, produced industrial, or agricultural sources prior to releasing it back into the natural environment. Or in some cases, the water is reused in industrial or agricultural production. Well, joining me today is Stanton Smith.
Hey, Dave.
Hey. Stanton is the Senior Vice President of Sales and Marketing, and he's also one of the 3 co-founders at Crosstek Membrane Technologies. Stanton is a 20-plus year veteran of the water industry. He's worked at companies such as Veolia, Water Technology, Nanostone, and CeramM. And get this, he holds a PhD in chemical engineering from Oxford, all the way Oxford.
No. Everyone's giggling when they hear that.
Yeah, well, I always love the thing that you're a Rhodes Scholar too. That's
I do drive those trucks well.
Rhodes Scholar. That's pretty impressive. So anyway, welcome, Stanton.
Thank you very much, Dave. Thanks for that.
Yeah. So Stan, I was wondering, tell me about Crosstek. Why did you guys, what do you guys do, and why did you start Crosstek with Bruce Bishop and Job?
Yeah, so I'd say this. I was the late part of the founding team. I joined a little later, but I always have had common ground with Job and Bruce, and that we really think that technologies should be used for treating water. It's the most important thing we do is make water for drinking, for society use, for protecting the environment. Ultimately, Crosstek's entire mission is doing membranes and water. It's pretty simple. However, when you think about what's out there in the space of companies, there are thousands of companies out there doing water treatment. What's our edge? What did we bring? Why was this company formed? And that real focus of our company is membrane technology, but also next generation, bringing it to the market, the hard stuff, the stuff that people don't want to do, quite frankly. We pick up the heavy lift of looking at the market needs, looking at the trends as best we can. We don't have a crystal ball, but we see these trends, these needs that not for next year or the year after, but the next decade or two. What are those trends? And we think membranes can fulfill that need, fill that gap. So we try to be a market-focused company, bringing water filtration technology that leaps the current state of the art. That's the mission. The mission is to be looking to the future and solving those problems, not just for now, but for, and not to be cheesy about it, but the next generation also thinking about the future of our children. Crosstek is really focused on that.
That sounds great. I know you actually said a couple things that piqued my interest, and I'm sure we'll get through them. Some of them is the next generation of technology. You also said being able to treat the hard stuff. So we'll talk about what that is, and of course we'll cover some of the trends. So maybe let's dive right into it. Today's segment is about water reuse, and so maybe the very, very first question for you is define, what is water reuse, and who cares about it?
Yeah, so there's an interesting term, reuse. There's some very specific names for certain kinds of reuse. In a very general sense, using water that's been used before can be seen as reuse. There's also recycle, which means not even treating that used water and using it for a lower use purpose. So just looking at reuse in particular. So not recycle, not using already tainted water for a lower quality purpose. What we're looking at is using water that is tainted, has some contaminants, treating it to a level that's required for a specific use. In some cases, it could be take this wastewater from municipal purposes, previously used for municipal purposes, and use it for agricultural use. Well, that's relatively commonly used. Some countries do that with about 80% of their municipal wastewater, such as Israel. Very much a world leader in reuse of water. But that's a very relatively easy reuse duty. Wastewater treated for something that's a fairly easy use. What we're really looking at is something that's made for purpose inside the fence of a facility. So we say, okay, this customer has a wastewater. It's really, really nasty, could be, but they want to make use of it for boiler feed water. That type of process is where we shine. We use that water. You get what you get. Those nasty outfall from their on-site production processes, and we have to make the magic between how bad that water is and what they want to use it for. And that entire process, that concept, that solution, that's what we do. That's reuse. Yeah.
And can you give me some examples of some of the customers that Crosstek is deployed in? Like, what industries are they in? Food or just some examples.
There's a wide range. So Crosstek's the last 5 years of our business, a lot of it has been focused on reusing the nastiest water, where, quite frankly, you would imagine is even possible. A large part of the business is around landfills and use of runoff from solid waste. That ends up being treated with membrane processes and generating a clean water and a concentrated waste effluent where all of the contaminants are put into a smaller volume of water. And so landfills, we have at least 50 installations of landfills. We have waste-to-energy facilities where they also take waste from human endeavors and generate biogas from it, and that wastewater gets used in a way that generates water that can be used for various on-site industrial purposes, including boiler heat generation from boilers and waste. So a lot of our work was in that very nasty segment of landfills. We then expanded to other industries that, quite frankly, to some other water folks might look like pretty intractable problems, but we've moved right into other industries seamlessly from very nasty beginnings of the worst wastewater there could possibly be. I know you're smiling, thinking, "What the heck is a landfill?"
Well, I'm smiling because earlier you used the term the hard stuff, and then you called it nasty water. And when I hear about landfills and I hear about runoff from solid and human waste, that sounds pretty nasty to me.
I can give you an idea what this looks like. I've been to a bunch of landfills. I know it's very prestigious. That's what Rhodes Scholars with PhDs do. So we went to this landfill basically in a suburban part of a big city in China, and we were surprised that they have it right there. And the reason for that is taking so much landfill waste that humans generate, which could be as your couch. What do you do with that? What happens? What happens with the stuff you put in the side of the street? And so you think, they probably recycle. A lot of it is still not recycled in many parts of the world. In fact, in some countries, the waste material from construction is blocking filling up landfills. They have to figure out different ways of managing all construction waste as they develop their countries. These holes in the ground that we're digging, that you're putting in solid waste, is filling up the earth. But in any case, what happens is you put some stuff in there that might be considered organic, soluble, miscible. And those materials end up in this landfill, and then rain comes into this landfill, and then it flushes out. And that's the stuff we're talking about.
That's pretty disgusting.
The most beautiful rainwater landing on this nasty stuff and flushing out. That's what we're dealing with. Yeah.
I mean, there are a couple other applications I was intrigued by. We talk about landfill and runoff, but also things like food and beverage, beer manufacturing, sugar manufacturing. In that, you really care about the quality of the water. Industrial waste.
Yeah, beer is particularly interesting because in the process of beer, and I do love a good IPA. We are in New England here, after all. There's a lot of microbrews up here. A very recent project includes a microbrewery where they said, well, it's interesting. It's interesting to say this. It's interesting to say that reuse is no longer a case of a necessary evil, but actually a source of revenue or source of cost control for some of these breweries. The one in particular, I don't even know if I can mention the name, but they are microbrewery, fantastic. I love the beer. Even my wife loves it. It's a high bar. They realized that the waste from the beer brewing is so concentrated that it costs them a lot to send that to a local wastewater plant for the town that they're located in. And that cost, which is, fair cost passed on to them, includes dealing with the biological cost of aerating biological treatment of that waste. So instead, they reverted and said, what can we do with this? They contacted one of our partners, and our partner said, we can do anaerobic treatment. What does that do? It's amazing. So they go from sending the stuff out by truck to a wastewater to treating it on site. There's capital cost involved, but it generates two things for them. Clean water, which can be used for non-food contact purposes on site, and they generate gas, natural biogas from this high-strength waste, and they can use that as a power source.
They actually reuse the gas?
So they reuse the gas on site to
Wow.
do. So,
That's
so
pretty
turning
efficient.
waste into clean water and gas. I mean, that's what what nature does anyway, and we're just concentrating it up. So that's exciting. That's a very good financial model for reuse. Right. Yeah.
And also, we have a deployment in a sugar plant.
That's right.
I was wondering, real quickly, how do they use water treatment technology there?
That's right. So that project also uses the same concept. It takes this high intensity food waste and treats it with biological treatment, but it's called anaerobic treatment, and they use the membrane plant to retain the biomass. So what we're really doing there is the membrane is retaining the biomass inside a closed engineered biological system. The biomass is really, really fine, and that kind of biomass is very difficult to settle with gravity or simple basic methods. And we put the membrane plant after the bioreactor in. I shouldn't say after, it's in concert with the bioreactor, because the flow goes between the two all the time. And that by doing that, we concentrate the biomass. The biomass consumes more of this organic waste per volume unit and forms the gas at the top of the bioreactor. And then the clean water from that is coming out of the membrane pretty clean. What the next step in that particular project is to consider putting one of our next technologies, our reverse osmosis technologies, right after that membrane. And the goal there is to try and make really high quality water for use in the plant. That next step is the first and we should talk about some of the details around running one of these facilities, because it sounds really great when a bunch of guys talk about it, but we can get to why reuse is sort of slow to move. But in that particular facility, they decided to do the first step: treat the waste, make power, and have good enough water to discharge to the sewer without penalties. And that's step one. That's a good first step. The next step is to put a secondary technology after that, a reverse osmosis membrane in particular, to recover that water to use it in the facility. So the first step was to offset the cost for disposal of high-strength waste by turning that into clean water for disposal and gas, valuable gas to drive the facility. And then the next step is to then come back to the table once they have their hands around this, that they know how to run this now, to take that next leap, which is to reuse that water.
Okay.
Yeah.
Great. So I know we're going to get into an example of some industrial reuse treatments, but let me step back a little bit and say at a macro level, I was wondering if you can talk about some of the trends that are going on in the reuse industry.
There's a lot of people that's very knowledgeable in this business. We look at it from our point of view, which is, what our point of view is simple. As population growth increases, yes, here we go, zoom out. You said high level. There's macro trends here. Population growth is just unstoppable. The human race is successful and growing. What happens is the average person needs 100 gallons a day of water. As we grow in population, we then place higher demands of water on our environment. So how am I getting to reuse here, right? We then waste that water because we don't retain it. None of us are growing at 100 gallons a day. So we waste that water, and that goes into the environment. We don't leave that water untouched, unscathed. We put various things in there. Deodorants, detergents, natural waste, all of that stuff. We treat that water, we put it back into the system. The funny thing is that system is the rivers. And those rivers now have more people drawing from them. So at some point, the flow of that river is starting to become limited. And so the macro trends are very simple from that analogy, that story, that sort of is that you can't draw from the environment in an open loop fashion. You can't draw from one river and dump to another river. It's the same river. As you put the water into that river, the quality of that river gets worse, right? So pulling more and putting more back means you're contaminating more. The quality of that water is decreasing. So besides the fact that there's volume limitations, there's also quality limitations. So the macro trend is very simple to infer from that. One, you need better technology to treat the source water because we are contaminating the source water much more with our intensive human population growth. You two choices. You keep contaminating and keep treating, or you start treating locally before you contaminate to avoid contamination, which is a better approach because not all contamination is friendly. Not all contamination is easy to clean. And sometimes that contamination shouldn't end up in a river and be distributed and diluted because now you need to treat a massive river to treat something that could have been a point source treatment somewhere where it came from. So all of that I'm just inferring from, the need for more water and more quality and higher quality of treatment for those water sources. So that's probably the highest level trend. Looking down, unfortunately, some of that contamination is in the water already. So PFAS is a popular one at this point in time. We're seeing some legislation coming up in there. The forever chemical being named that because it just hangs out there forever. So once you put it in, maybe it happened in the 80s. Maybe it happened in the 90s. It's there. It's not going away. Nature can't deal with some of these fantastical new human micropollutants, as we call them, that we add to the environment, the system. And so you think about that. Now it used to be a simple old water plant. I went in, I pulled water out, I put a little bleach in, killed the bugs, killed E. coli, I drink it. That's starting to disappear. You start to have real demands on your water plant at this point. Now we're seeing massive systems that are being built for dealing with contaminants that never existed even 50 years ago. Yeah.
So, you touched on some of the macro trends. Of course, we've got to reuse the water because conservation of mass means that the river is only so big and we consume it and it's got to go back in. So that's one of them. Another one is purity. Another one is being able to treat for future contaminants like PFAS. So maybe a question, these are some of the macro trends that we might see overall. Maybe some questions for you is tell me about some of the macro trends in new technologies that are going to be meeting some of these ecological challenges that we're seeing.
So, of course, we're biased to membranes, but we also see ourselves as solution providers. We think that membranes represent a good backbone for a company. That's kind of where we came from. Also matches our skill sets, let's be honest. When you think about what you can do with your knowledge, membranes and water treatment chemistry and jumped out, right? So what we're dealing with here is a bunch of challenges that are new, but also have to fit into an infrastructure system that's kind of known and in a way very difficult to change. So innovating disruptively in water, wastewater is an interesting conundrum, right? What I mean by that is I can't just come out of nowhere and have this completely new thing and say, this is the new thing. It's very difficult to innovate in water. It's an industry that's huge. It's huge. It's bigger than you think. And I recommend people to look at the size of this industry and tell me if you think in your country there's not at least 25% of the economy related to water. It's huge.
It probably is.
It's so huge. And it's also what makes it difficult to innovate in is the legal system around drinking. It's more difficult in some countries than in others. In the US, we have the state-by-state protection of the people written right into our constitution, right? Give you an example what I mean by that. I bring something new to the market. I got to make sure it meets federal requirements. which pertain to it. And then I got to go, in order to sell it to each of the 50 states, I got to make sure it meets the state requirements for 50 states. There may be some that gang together. There may be some that defer to the federal regulation. But the point remains, innovation is challenging. Now, what are people doing? What I feel, as a nerdy PhD student from years ago, and I retain that core, is that people do the right amount of innovation at the company level. We probably need some radical stuff at the government level, but if we do remember in the US, the government of the US funded the development of reverse osmosis membranes. That was a big deal. There's an example of radical development. And the government still does some programs through DOE and various new programs that are coming on. It's very nice to see that. But what we are doing and what we're seeing in the trends is that people are innovating within a sort of structural framework of what people do at a drinking water plant or a wastewater plant, and we innovate inside the fence. And that's what we do. And it's fantastic and challenging in its own. But our focus, what I've seen in the trends, is that there are two big trends going on in innovation. One is there's much more government funding right now for completely blue sky development. I love it. I see it. I'm excited, and I would love to be a PhD student now, but I'm good. Okay, but then there's a load of innovation going on inside the fence of a drinking water plant, a wastewater plant. And that's what we focus on at Crosstek. And that kind of trends include different materials, different configurations, and different ways of doing what you used to do that involve retrofits, improving, changing. So I think that's just to be honest, there's two big trends, two major trends. The last 3 to 5 years have seen major funding into blue sky, new ideas, and that's wonderful. In the industry, a lot of the work is working inside the existing infrastructure and making it better.
So anyway, you've talked about some of these trends in the industry. I'm also curious about, what are some of these new technologies that are out there today, and maybe some of these things are what Crosstek does.
Yeah, absolutely. So I think that's the key. So we're getting closer to what we actually do here, how we use that industry knowledge to what we do. I'd say this: there are two major trends happening right now, very exciting. One is that we see a big government-driven and big organization, an NGO-driven fund that's starting to say, give me something new in the water space. Give me something radical. Be crazy. I'm not asking you to build a business. I'm saying just go crazy. Okay. High risk, high return. So that's nice to see that coming back. Like I would say it's nice to be a inventor right now, a PhD, a scientist. It's a good time. Okay. So I think water is experiencing a little bit of a renaissance there. We all should remember that the US government was particularly vital to developing reverse osmosis membranes. And it took 10 years to get out of university, and they kept funding it. And I bet you it would have been interesting to be a fly on the wall when someone says, that is just crazy, that's never going to work. And today, it is displacing thermal technologies, right? So we gotta look to the past to see what we need to do and energize that kind of invention. Now, inside the fence, inside the existing infrastructure, because we happen to have 6 or 7 billion people running on water systems already, right? What can we do inside that fence is a lot of the other stream of work, not completely blue sky, but something that's closer to helping in the next 5 years, right? And so we have sort of 5 categories I want to touch on there. First one will be materials, right? New materials, absolutely exciting. I mean, if you're a material scientist, good God, everyone must be a little jealous, right? You got ceramics, which is starting to show real signs of adoption in the marketplace. We definitely focus there, and we can touch on that a little more. But then there's ceramic features being rolled into polymeric membranes right now, which is unbelievable, right? I mean, think about that. It's just so saying, why not just combine those two and use the best of the ceramic to make a better polymeric? Then we got configuration, so changing products to look, feel, perform a different way. So what used to be a locked-in system, you can now say, I can replace that thing exactly in your infrastructure and give you a better performance. So configuration changes. Then we have a system and product optimization. So, that is interesting because that needs a lot of knowledge. It could use the same product inside the system with a new innovative way of operating, right? And there I see ROs as showing a huge impact. I take my hat off to a company called Displace, who spent a ton of time convincing the world that ROs don't have to be boring and run in one place all the time. Although most RO operators say it's not boring, I have to do so much stuff for it. Displace, and I was on the other side of it, watching them going, this is crazy what they're doing. I was on the big company side, water operator side, saying, this is outrageous. You know what? Few years on, sorry to those guys from Displace, when we were skeptical at my former employer Veolia, that was good work, and we and Crosstek are looking at that and taking a page from your book. So there's product configuration, product and system optimization going on out there. Then we have retrofit. I brought that as a separate category because retrofit uses all of the above in different ways. It uses different configurations, improve performance within an existing system. An example of this is you go to a fast-growing community, and even they were surprised. Oh boy, I have more people here now than I had a year ago. And the regulations say you need to have so much capacity per person in your water plant. How do I do that quickly is often the question we hear. Well, there's two ways. Let's look at what you got. And retrofitting equipment, existing equipment, a specific example, we'll take out media filtration and stick in membrane filtration into the same basins. Huge flow improvement, right? Within the same civil engineering construct, we can double often the capacity of that facility without having to do an excavation, building, construction project. Huge improvements. And to boot, you get better quality. But hey, I'm not against media filters, I'm just saying. These are membrane. So that's kind of the first four. And then the last one that probably is, I don't want to use the word hampers, but is a challenge for all of this, is the legal structure and regulations around putting these technologies into the market. To this day, and this bugs me, that membranes are still regarded as alternative technologies. I mean, it's been around for 30 years. I feel like anyone who hears that word in my position would say, yeah, that's a little much, right? It's still an alternative to the other stuff. And that is, if you look at state regulations, a membrane code is an alternative. So you need to know that you're not the main thing.
Okay.
So there's a lot of things that I'm talking about there, but those 5 topics really are what we see.
So you told me about you told me about some market trends. You told me about 5 technology trends, new materials, more efficient ways of doing configurations. The second one, third one, you said system optimization of things. The fourth one, you said you got to be able to retrofit that. It's got to fit within existing infrastructure and walls. And the fifth thing you said was legal and regulatory issues that people must consider. So I'm going to take those and maybe ask you the next question, which is...
Make a little smoothie with them, huh?
As long as it's not sludge or that nasty stuff.
Exactly the kind of
that
smoothie
nasty
you get from
stuff
that.
you get. Actually, I've seen it. It's nice and brown. Looks like a root beer float. But so we talk about some of these macro trends. Okay, you're at the operator level. Mm-hmm. You are a plant operator. Either you're going to retrofit something or you're going to build something else to do reuse. Tell me, I mean, what are the key considerations, or what are some of the things that these plant operators are considering when they're building a new plant or retrofitting with new equipment, new filtration technology?
Yeah, I want to say this, Dave. You ever seen the first people that went to space? Those guys, they were just guys who had a helium balloon attached to them, and they floated to 69 miles, right? You just took me from there to the ground, and that's what it's about in water. Knowing the trends and then knowing what a day-to-day life of an operator is, that's probably something that comes from the fact that we worked in companies that owned and operated plants. So you just dropping from space down to the ground. And I appreciate that question, because here's what it is. That's the crux of the reason why reuse is not the first choice that someone will do. It's so tough to operate a badly designed reuse plant that I've seen them turned off. Even plants where we have our RO systems running, I can sometimes walk in saying, why are you not running the second stage? Or why are you not doing this? It's very tough. When you design a plant for reuse, in particular reuse, you got to look at the operator's day-to-day life. So many of the people we're selling to see water as a pain in the butt. They make I don't know, engines, semiconductor chips. I mean, this is some good stuff. They don't really want to have to think about water on as a part of their life, right? And so the question is very important. I think to answer that fairly and properly is that I want to say there's this sort of operator as an owner and operator as the boots on the ground operator. So let's look at both of those point of view. As an owner, CSR or corporate social responsibility is actually real. I'll say that to whoever listens to this thing. It's real. We have sold systems to people that have more water than they know what to do with, but they want to reuse because they want to show the investors that they care. And I scratch my head because 10 years, 15 years ago when people said that, they never really went beyond the point of budgeting or something, PowerPoints. They were PowerPointing the hell out of that reuse job, but we never built it. To build a reuse plant in upstate New York next to the Great Lakes that has more rainwater on their facility than they know what to do with was a pleasure and a surprise, but now it's a trend. So I want to say that the drivers at the operational level are CSR big time, but here's the part that's important. They actually are not wasting money anymore. Yes, the ROI, the paybacks can be low, because in a water-rich environment like that, the cost of buying water is pretty modest. But they still have paybacks. They're not cost centers. Okay.
But I mean, what are some of the, you seem to imply there are several cost centers or factors that go into that ROI, whether it's operating cost or initial capital purchase of equipment. I was wondering if you can talk about some of those.
Yeah. I've seen a number of these analyses, and the nice thing about working in the industrial space is that you get really close to the customers. It's that they want to understand the project very well. They want you to understand their desires very well. So you get to see their goals, the 2020 goals, which are now implemented, the 2030 goals. So there's a number of things. One, your corporate role. You see yourself as a person, a company, an entity that wants to do the right thing. I really think that's primarily a start of this conversation. But then once that big wig walks away from this meeting, because he just grabs the coffee and sandwich and walks away, I'm dealing with a facilities engineer who looks at me and goes, this has got to be not a full-time job, because I actually make engines or I make airplane wings. And I don't want to have to hire 7 people to do this, right? And let's talk about this. And so then there's that level, right? I am paying for this thing. I also do not want to hire a ton of cost, add cost, and all of this. And then there's the next level down, which is ROI payback analysis, which comes from the finance team. They say, does this thing actually have a payback? Because you still have to have a justified business model. You can't say I'm paying 50 cents a gallon to treat this water, and I'm saving me 2 cents a gallon. It's just a difficult equation to do in perpetual loss of money for this project. It's not a reasonable position, right? So what we've dealt with is we always model the ROI. So what does it do? We look at everything. How much power? How much water can you really recover, and what's the new source? Each source has to be considered, right? So each source of water, because they have varying sources. So you have municipal water on every site, okay? And then you have industrial water on every site, right? So from the various uses of the water, the contamination levels are different. And then you have to match that source to an end use. And there the regulations play big time, right? I'm not going to make drinking water, probably, right? So you'll still be buying drinking water. Are your bosses going to be happy with that, right? And then what do we have? What are the big uses around your plant, right? Boiler feed water. Okay, cooling towers. Okay, these flushing toilets. Okay, so you go through all these things, right? And then you match those. Match front end, match back end. Once you match those, you got quality and volume criteria established. Now you say, does that add up to a percent that I achieve my goals, right? 20% reduction, 50% reduction. And then from there, you move into, okay, now to achieve that treatment, like we mentioned earlier, connecting the incoming water and the output quality, you design a treatment plant. And you design that treatment plant to match the quality, and you measure the power, the operational intensity, how much labor do you need, the consumables, media, membrane filtration, chemical cleaning. You every single inch of the way gets measured and modeled, and then you present that, and the final meeting, and a budget, and the customer says, that works. Awesome. Let's do it. 20 years ago, it never worked.
Okay. Cool.
Yeah.
You know, I know that you and two of the other founders, Bruce Bishop and Job, you recently published a paper for the AMPTA membrane conference. Was wondering if that's something you can talk about.
Yeah.
What was the paper about, and who was the customer, and what were some of the considerations that you talked about in that paper?
So this paper is I hope those who attend the show come and see this one, because I like this paper in particular because it shows a few years of experience, not just design and sale but actually real experiences, things that didn't work out as we thought, things that changed as we operated, and stuff like that. So, due to confidentiality of the customer, I can say that they are a major engine manufacturer, and they you probably know them. They have a good CSR policy, and they really want to do the right thing. Okay, so that's the company. I would say, first thing I'd say is corporate responsibility initiated this project, period. There was no other reason for this. This is a company that basically had to add in multi-million dollars of equipment to do the right thing and add stuff to go with it in an environment where there's more water than they know what to do with, to buy it at low cost. So that was the driver. The project itself is about as full-fledged as you get. I can't imagine. I think I might have called it lead to gold in some LinkedIn post I did the other day to promote it a little. But yeah, it's literally the worst water that you could possibly think of in a membrane filtration system.
So the water was, what was they were trying to treat the water that was a result of the manufacturing process.
Manufacturing, yeah. So I'll tell you what the water is. This is massive engine blocks being machined from flat steel to shaped steel. And to do that, it's real intensive spray of a combination of water and oil on the surface of the metal while the machining happens. CNC machining, we've all seen it. You spray lubricant and coolant combined, which is water and oil, onto this machine, and they just make hundreds a day, hundreds of these engine components every day. And then they do dye penetration testing and various testing, and all of those wastewaters come in as well. But this is water that looks like a milk, creamy emulsion, not a very drinkable milk, but it looks like a perfectly mixed water and oil combination that is intractable. If you set it down for 5 days, it would look exactly the same. There's no oil floating. It's intractable, oil and water. We call it a stable, chemically stabilized emulsion for all intents and purposes. Not many membranes can treat that, so what we did was we put that in. So that's basically 50% of the water that we treat. The other 50% is the 2,000 or so staff members that work there, canteen activities, just human waste coming in. They call that sanitary waste. I always laugh about that. The industrial guys call that sanitary waste. That tells you what their real industrial waste looks like. So we got this sort of engine block stuff, and then we got the sanitary waste, and they segregate those because they need different treatments. And so this particular facility takes this really hardcore engine oil, and they came to us and said, let me not take credit for everything here. Crosstek is amazing. Yes, we are. But these guys always used ultrafiltration to treat that since the 70s. Unbelievable. Maybe 80s, 70s, 80s. We walked in there and we just saw this, clearly 80s technology. There was a beautiful, literally 5 foot tall by 10 foot wide control box with light switches on it, with relays switching controls. It was like a museum to control. But they used ultrafiltration, but they needed to do more with less space, because now they were going to add in a whole lot of reuse equipment into what was just a discharge plant before. And so, Crosstek basically came in, took that industrial waste, applied ceramic cross-flow membranes to treat it into a oil-free, and I should say emulsion-free solution that was then ready to go to biological treatment. So it goes from there to biological treatment to consume remember the ceramic ultrafiltration removes particles and oil. What's left is dissolved material that's biodegradable. And so the biodegradable part was then mixed with the sanitary waste. Remember what we call sanitary waste? Earlier, blended together and fed to a membrane bioreactor, so another membrane plant, which was designed to keep bugs in a good concentration. And then the effluent from the bioreactor then goes to a reverse osmosis plant for 90% water recovery. And that 90% permeate goes back to two major applications: cooling tower for cooling the facility, the production facilities, all the machining needs cooling, and to boiler feed water to produce power, to produce steam around the plant for production activities.
So I think what I heard you say is their existing ultrafiltration, which they've been using since the 1970s, and maybe explain, what was it missing? Was it just it was not properly breaking down the oils? And so I guess my real question is, you talked about this old technology using, or old configuration, I should say. They have this ultrafiltration, and what did Crosstek come in your paper? What did you add?
Yeah, good question. That technology was cutting edge in the 70s and 80s, and if you don't mind indulging me, we can speak about this for 1 second. Crosstek CEO Bruce Bishop, many years ago, started working in a company called Ceramem. Ceramem's founder, now here we go back another generation, was the first employee of a company called Abcor. And Abcor, in the 70s and 60s, invented this tubular UF concept. 60s. So the CEO of Crosstek was the first employee, I think, for Ceramem, but the founder of Ceramem was the first employee for Abcor. And those tubes were the bee's knees in the 60s. No one could do what those things do. They were amazing ultrafiltration membranes, and believe it or not, they're still in use. But the problem with them was walking into the engine facility was that they were just huge, just unbelievably huge. A lot of what we're doing now has to address more than the beautiful science. It's got to address retrofit. It's got to address existing facilities, especially in the US. People don't like to break out concrete walls to do stuff anymore. If our reuse project had another building that had to be built, that might have killed it right there. So instead of doing that, we saved about 60% of the area, floor space, for that wastewater building by changing technologies. Same concept, ultrafiltration, same even process configuration, cross-flow. But we went to something that was, 50 feet by 30 feet to something that's a quarter of that. Now you've freed up enough space to do the other water treatment that enables you to do reuse in that same floor space. So that was a major step for that. And that's one piece. The second piece, no building means lots of savings, right? The second thing is we were more reliable. Materials have changed. You went from a polymeric membrane to a ceramic membrane. Ceramic membranes in their very nature are hydrophilic. Hydrophilic being oil-hating, water-loving. And so that emulsion would routinely clog up those tubular polymeric membranes, and the cleaning frequencies were pretty high, okay? On a production site like this with over 50, 60 different production trains spitting water out at any one time to the wastewater plant, you got to be nimble. Ceramics are robust, they're cleanable, they offer an improved materials almost optimal for oil emulsion treatment. So it's a combination of retrofit, right, and materials and configuration change that really moved that forward.
So what were some of the key challenges at this engine manufacturing plant as they were considering upgrading their equipment?
Yeah, Dave. So I said this. That would have been started in 2015 when this discussion started with the customer. They had two things happening at the same time. One is they were formulating their corporate social responsibility goals, and they said we got to achieve these certain water reduction requirements. So that was part of the driver for this. The second driver was that this plant was built, in the 70s and had a wastewater plant which was dating to that time. And their wastewater plant at that time had simply two pieces to it. It had treated the industrial wastewater with an ultrafiltration system, circa 60s technology, and then also had a post-ultrafiltration system to treat the dissolved organics in the ultrafiltration filtrate as well as the sanitary waste on site. That was made simply for discharge to the local publicly owned treatment work. So here we have a plant that's already in existence for 40 years, and they do discharge to the local city, and they want to take that and create a brand new recycle plant, because they've now decided that they need to do better and more for the community by reusing water. So all that said, now you've got to think about all the million things that go into that. You have this building, a wastewater building, with a limited footprint. When we walked in there, we couldn't believe it. This beautiful 1960s technology took up half the building, right? But it was ultrafiltration, and it had a bunch of problems associated with it. It was old, it was aging, it was operating intensive. It was made of polymeric membranes, which was the only choice in the 60s and 70s for treating this kind of wastewater with emulsions. But the time has arrived, pretty much 20 years already. By that time, ceramic membranes have been used. So, it was ripe for change. It solved two problems by doing that. We could engineer a system which is much, much smaller. So now you freed up footprint for installing additional equipment for reuse inside the existing building, saving a lot of money and just time to achieve your goals, construction cost and construction time. So we hit that goal there. So you're hitting sort of the key things we were talking about earlier. You're talking about existing infrastructure retrofit. You're hitting improved performance and better materials. You're hitting sort of operator intensity reduction. So you kind of look at those goals and they come right out when you apply the right technologies. I should state that the incumbent membrane product was still a strong company and still in existence. And they were part of the evaluation. So what was in their favor? They've done it for 30 years with that thing. They know the enemy they're facing. The new technology to them was new, ceramic membranes, had to be proven.
So you mentioned several things. One was the existing footprint. It's not like they're going to build a new building or expand things. So big advantage to fit into the existing space.
Yeah.
But in that existing space, the new technologies, from what you're telling me, smaller footprint, allowed you to add in new configurations, which made the whole system much more efficient.
That's right.
And materials
underpinnings of success of this project was the ceramic material.
Ceramics. Yeah. So it was all about ceramics against polymeric. And that's I assume correct. That's actually...
That's a theme in our day-to-day living in Crosstek, right?
And is that what's going to be presented in the paper? You're going to be discussing
correct.
Those?
We're going to be discussing those, and I'm pretty sure that there'll be lots of questions, because that is the dilemma or the question of the day. So here's the funny thing. Everyone loves ceramics when they hear the technical aspects. Right, I remember presenting ceramic membrane solutions in the early 2000s to people saying, this is perfect, look at the performance, we got an installation somewhere, and they just look at me and they go, well, what's the price? Because back then, they were so expensive, they had nothing in their favor, no scale, no adoption, no real broad-based supply chain. And now, it's different. We got volume on many of these supply chains, we got better pricing. They were never questioned technically. They were just like, oh, well, we might as well make it out of gold then.
So the prices come down.
The prices come down.
And that's, in a way, you're saying that's why now is the time.
It's the time.
It's the time because
and I
the
think
prices
people will
come
see
down.
the value is right. This particular project was nice indication on that front end on the UF portion, because it was UF to UF. I felt it was an unfair evaluation because they didn't give us the building savings.
True.
But they said, well, let's just keep merit to merit, they called it. I'm like, wait a minute, we saved you a building. Anyway, it was still, so what happened was the ceramic membrane was capital 20% more capital, but the life cycle saving over 20 years was 30%, including the high capital. And the operational intensity was a fraction. It had better warranties, because it's pretty easy to warranty ceramics now, because the conditions of operation these things are baked to 2000 Celsius, okay? You're not going to wreck them with anything you're doing in water and wastewater. So a lot of it was giving them comfort. The demonstration, we performed a 1-month demonstration on site with a small version of the technology, showed them the power, the membrane capabilities to perform as well or better. So a lot of that demonstration occurred in on site. A lot of it was to give the site comfort because it's hard to turn away from something you've done for 20 to 30 years. And so we understood that and we did that. And no matter what people say, you never make money on demonstrations and testing. You lose money, but it's worth it in this case because we've earned the customer for life and we are building similar facilities at their other, similar technology into their other facilities as well.
So what you're saying is a lot of these results were or are currently quantifiable.
Absolutely.
And you also talked about the pilot that was run for about a month, but also how long has it been in operation for?
Yeah, so I went just after startup because I'm trying to think. So it's been in operation about 3 years now, if not more, and running full time. This is one of those that there's no other options when you have emulsion. You got to run. There's no like, oh, I'll just put it into a bucket. This project is fantastic in that we are doing two things. We have concentrated that oil emulsion. We don't disappear the oil to something, we concentrate to a volume that's so small and so concentrated that someone can put into a burner. So, 20 to 30,000 gallons a day of water being turned into something like 3,000 gallons a week of concentrated oil. And it just gets removed as a small weekly dump and someone just puts it in a burner. It's that concentrated. So, so it's kind of an interesting way of getting rid of oil.
So from the results, 1 month pilot, then it's been deployed in production in operation for the last 3 years.
Yeah.
So I assume the customer is happy?
Customer is happy. We are getting the second project undergoing with them. I credit to the facilities engineer at that site who said, I want to do this. It's different. It's easy for him to say, I'll just do what everyone else has done before. So he's a wonderful ambassador for a person whose main focus in life is not water, but looked at it and said, I think I want to do things better. So there's definitely credit there to the end user. He's not a fast follower, but an early adopter. It's very important. And then we have the performance of the system has been extremely, let's say, satisfying. It's performed. There's bumps in the road. Believe me, we lost one cross flow pump. There's 2 cross flow pumps. And there was this operational challenge, and we got this call saying this thing is not performing well. There's always those moments. We go out there, we solve the problem, it comes back on. We do some deep cleaning for a couple of days. We do some pump management, put some more sensors on to make sure when this happens again, it doesn't cause a problem. So, but this is the real bumps and knocks of a reuse plant. But as far as it goes, that's about the worst thing that happened, and it's running for 3 years. I'm pretty happy with it. Membranes are still in place, the exact same membranes.
So it's running for 3 years. You've got repeat business. It's all quantifiable. The numbers are there. These are all things that you're presenting in the paper at AMTA.
That's right.
That's pretty awesome. And so actually what I'd like to do is conclude this podcast, and thank you for all of your insights. Of course, what we really would like people who are listening to this, we invite you to listen in to some of the presentations that the Crosstek team is doing. This is actually one of them. This case study.
This case study is one of them. And it will expand to the reuse portion as well. I was focusing on the fantastic, front end of the process, but there's this sort of bioreactor and then this 90% RO. Considering, like I said, lead to gold, the nastiest water you can ever imagine, becoming boiler feed water, which is kind of the highest quality of water you can feed into any equipment. So it's a lead to gold story, and it's pretty fascinating because there's actually years of data to share. And you can ask the presenter, please ask the presenter, our CEO, who is actually presenting a paper, because he was really instrumental in getting this up and running in the early stages. He's from that part of New York. He wanted to definitely have
that's right.
something,
He's from upstate New York.
Something for where he came from. So he was definitely on site as part of this. He was very excited about it, to be in like 20 minutes from his hometown where he grew up. And of course, he's a Red Sox fan now. I don't know if he's allowed back. But I think there's two other presentations from Crosstek. We have 3 podium presentations. We're proud of it. We and they're all exciting, new stuff. That's what we do, and we have a poster as well. And I'm having the privilege of presenting a roundtable on ceramic membranes. So if you want to pick my brain about ceramic membranes, it's not much there, but come bring your own stuff to share, please, and I'll be happy to lead that session. It's also part of the show.
All right.
Right.
Well, thank you very much, Stanton. And we will look forward to seeing people at the presentations that we have. And please stay tuned for our future podcasts.
Well, thanks, Dave. You did a great job in this, extracting useful information from me. That's unusual and difficult.
Thanks, Stanton.
Thank you.